Helios, over to you.
Thank you very much, Sean, for this introduction. Let me start by saying that I was very pleased to be invited. I thought finally a live meeting again, nicely postponed to early 2022, but here we are still online, which is a pity, but let's make the best of it. So I will talk about solid-liquid interfaces from the perspective of growth. So I will briefly explain why we're studying this, and I'll discuss the two systems that I aim to discuss, which you see here, gallium nitride and calcite. The work that I show is in fact a collaboration. It's a thesis work of Arjan de Jong, where we collaborated with several people that I list here. I won't mention them all. And calcite was done by Sander Brugman. You see the photograph, and also that is a collaboration. And you'll see more details as we get along. Now, the context that I have here is crystal growth. In fact, this is the topic of the group that I'm working in. I'm heading, in fact, and growth is something that relies on a huge amount of parameters: supersaturation, temperature, pressure, lots of things. I have a list here, which is not even complete, but one of the parameters, and this is the surface and interface structure. I'm not claiming here this is the dominant parameter, but it's one of them. That's the one parameter that we're going to focus on this afternoon in my talk. And of course, crystal growth happens at the interface. This is where the action is. And depending on the interface, and I'm actually going to talk about solid liquid interfaces, the medium is a liquid solution or melt, and the crystal, of course, is a solid. And both sides of the interface will typically deviate from what they are in the bulk. So the crystal surface may relax, and certainly the liquid will feel the periodic potential of the crystal, and so you have some ordering properties there. And this is what we want to address today. And the techniques that you could potentially use, you should never use one technique. Of course, I will today focus actually on X-ray diffraction, given the topic of this meeting. But you could say in recent years, there have been quite significant developments in atomic force microscopy, in particular frequency modulation, AFM, which allows also to see the ordering properties of the solution. There have been significant advancements in computer simulations, and what I'm showing here is a fairly recent result where X-ray reflectivity has been combined with simulations and gives you a more detailed picture. And X-ray diffraction actually has been a technique has been around for quite a while to look at such interfaces. And so what I want to do here is to combine as much as possible. Now, I said this is relevant for crystal growth, but actually this is only to a limited extent what I'm going to describe, because in fact, if you look in detail at how a crystal grows, then the action is always at a step, and actually even more precisely at a kink. So if you really want to know what's happening, you have to zoom in on such a detail, and then you need essentially microscopy or computer simulations. And the technique that I'm going to use, X-ray diffraction, is pretty useless for this, unfortunately, or that's the way it is. So instead of immediately going to something highly relevant, and some progress is being made there, what we're going to do is to look at something far more simpler. So in that sense, also less relevant directly for crystal growth, which is a completely, well, as flat as possible, completely flat surface. And if on such a surface we can get consistency between the observations of microscopy, computer simulations, and X-ray diffraction, I would argue that then you can start believing what the other techniques are saying on a more microscopic scale, and that will help in understanding what's happening. Actually, diffraction might be able at some point to look at the microscopic scale. Of course, we have fantastic developments in X-ray, free electron lasers, and things like that. But that's not what I will talk today. And the technique I'm using, it's almost embarrassing to bring it in this conference because I'm sure that the vast majority of the audience is completely familiar with this. But the technique we're using is X-ray diffraction, interface diffraction, and we rely on crystal truncation rods and the fact that if you have a flat surface, the X-ray diffraction pattern is a combination if you like, of the 3D Bragg spots with the rods that emanate from a two-dimensional system, and at the merge of them is the famous crystal location rods that smoothly join the Bragg peaks, and the surface sensitive information is in between the Bragg peaks. Avoiding Bragg peaks is the way to become surface sensitive. This has been actually around and realized already by Max von Laue back in 1936. But the application of this as a practical tool is far more recent, because you need synchrotron sources to be able to do this practically. And just to, for those who are not so familiar with CTRs, here's a brief theoretical example that shows how this works in practice. So this is an example of a bulk cubic crystal, as simple as possible. Everything is bulk-like except the top layer, which I've drawn here, is supposed to be 10% contracted. And if you look at the corresponding crystal location rod, then without the contraction, you get the black line. And with this 10% contraction, you get the red line. And I'm sure you will agree with me that deviates considerably from the black bulk line. And so you're quite sensitive to something like a 10% relaxation. And in a similar fashion, we can look at more complex interfaces. Okay, let's immediately jump to the first example that I want to discuss, which is gallium nitride. And gallium nitride is in fact semiconductor number 2. It has a huge market value, only second to silicon. It's used these days for LEDs, Blu-ray, power electronics. And one way, actually not the dominant way, but one way to grow these materials is from the melt. So you have a sample in a gallium liquid. And this requires relatively high temperatures and pressures depending on how you do it. And this is a side view of the gallium nitride interface. And it actually is a polar system because you have these nitrogen and gallium layers. And we're actually going to look at the top face here, so where the outside layer consists of gallium. And to study this system, we constructed a special interface chamber where we can obtain temperatures up to 1,000 degrees, pressures up to 50 bars for ammonia-resistant materials. And in order to access the solid-liquid interface, we actually have to penetrate several millimeters of gallium. And therefore, we used high energy source 70 keV X-rays to get there. This is actually far from trivial, but I'll spare you the details. We had lots of runs, but eventually we managed to actually get reliable results on a well-prepared surface, nice and flat. And we had excellent data between 20 to 850 degrees C and from various pressures of nitrogen. And what I show you here is the data, which are the black dots. I show you two curves. The blue curve is just for comparison what you would expect from a bulk terminated gallium nitride sample, and obviously the data is very different from, or quite different from that. And the red line is the result of the fit that we came up with, and that contains both the solid but also the liquid part. And that's what I will describe in the next few minutes, exactly what we have learned from this interface based on this data and modeling. And so this is again a side view of the crystal. We start with the crystal part. And so, well, you could say this is actually, in our view, a simple structure, as simple as you can, because we don't have a solution where lots of things are mixed. We simply have gallium, so you expect things to be relatively simple. So it could be simply some gallium on top of the bulk terminated crystal. But it turns out from all our modeling that things are not as simple as we would expect it. So what we find, and we would say beyond any reasonable doubt, is that turns out that the top gallium of the crystal, there are 20% vacancies. This is not what I had expected, but this is really what the data tells us. Secondly, in a top view, you have this grid of gallium nitride, and you have these hollow sites. And quite often, if you have a liquid on top of such a thing, it's like an egg carton. The atoms are simply expected to be all over the place. So like this would be a full monolayer of gallium, liquid-like, but still full monolayer. What do we find, however, is this is not at all the case. It's about a third of a monolayer. So what we of course measure are average occupancies, but the average occupancy amounts to 1 out of 3 of those sites is dynamically occupied by a gallium atom. Not what we had signed up for initially. And then if you go to the next layer, so this is again a side view. So this is the 1/3 layer that I was just describing. And the next layer is actually has a higher density, 1.3 monolayers, with less ordered atoms. The size of the ellipses here are a measure of the thermal disorder of the liquid. And so this is a liquid-like, more liquid-like, and the next layers become even more disordered. And so you get quite a full picture of what's happening. So this is a top view where you see the same thing. So this is the missing top layer atoms, the partially occupied hollow sites, and then you see the things as we progress along. And so if we look at the full interface structure, then we actually find that you have quite a lot of layering if you go up. So this is the density profile that we model and fit. And the most interesting part obviously is here. And as I already showed you in the previous graph, you really get lots of details, bond lengths, etc., etc. So we learn a lot from this interface. And so in summary, what we find here is this simple structure is not as simple as we originally anticipated. More things are happening than we at least expected. So we find gallium vacancies in the topmost gallium nitride layer. We see a surprisingly low density in the first liquid layer, then a more dense layer in the second layer, and then a smooth transition towards bulk germanium. Gallium. And so this is more complex, but still a very detailed picture that hopefully is now something that can be addressed with other techniques like computer simulations. Of course, this is something that is difficult to assess with a technique like atomic force microscopy because the conditions, high temperature and high pressure, are not so easy. So this is something where X-rays excel. Okay. This brings me to my second system that I want to discuss. And this is, you could say, a bit of the other extreme because gallium nitride was supposedly simple, but it wasn't. Calcite is something that has been studied enormously. Calcite water interface is a highly relevant interface. It is very relevant for biomineralization. It's also, of course, you can also find it in inorganic forms, and you can actually make beautiful crystals. This was bought in actually one of those crystal shops for healing power, but they sold very nice crystals, so we use those to cleave and make very flat interfaces. And the aim of this study, of our study, was to compare state-of-the-art X-ray diffraction with computer simulations. And to a very large extent, this is an extension of work that was done earlier by Paul Venter and Julian Gale. Paul Venter did the X-ray reflectivity and Julian Gale did the computer simulations. And what we wanted to do is to go beyond reflectivity, use complete crystal location rods, so we do not only map the projected electron density, but also the ordering along the in-plane direction. And in addition to that, we also wanted to study the effect of ions, divalent ions in particular, because there were reports in the literature that these affect the growth properties and in fact even the liquid ordering properties based on AFM data. So we thought, let's have a look at that, see what's happening there. And just to illustrate what we would expect is happening, this is a calcite 104 surface, and so this will be where the crystal ends. And obviously, as you can see here, there are bonds that have been broken if you cleave the crystal, and you really cleave it to make a flat surface with a hammer and everything. Where you cleave it, these are bonds which make the surface unhappy. So you would expect the system to bond to its environment, and the environment that we first present is water. So you would expect water to more or less be in those positions. And in fact, the hydrogen is then expected in the position that we show here. And so that's the expectation, and that is exactly what we find. So no surprises here. What I show you here is the data. So in a very similar fashion. So in blue we see all the data. We still quite an extensive set of data on this particular system. In red, just as a reference, is a calculation for a bulk terminated calcite surface, and clearly the data is very different from that, owing both to small changes in the bulk of the crystal, but in particular to the bonding that you find in the liquid. Now, this model that I present here is by no means original. Many people have studied this also with X-ray diffraction, so we agree with the literature. The reason why we started from scratch is that we wanted larger data sets, and so we could do the comparison with the molecular dynamic simulations. The data I show here was actually obtained at the Diamond Light Source beamline IO7. Now, so and as I said, the aim was to compare this with molecular dynamics simulations or computer simulations, but and so I will show some graphs where I show positions as we derive them with the computer simulations. But let's first familiarize ourselves with how I present this in a slightly, well, maybe not so appealing way, but this is the best way to present it. So this is the model as I already described, where we have here the bulk crystal, and here is the bonding to the water molecules. And what I show here in purple is the positions that correspond exactly to the bulk crystal. And in purple also here you find positions if the bulk crystal would continue, which obviously is not the case. But what you find from our model, from the fit of our X-ray data, is that indeed in the bulk, the atoms pretty much stay in place. You see small relaxations. This is an angstrom scale. You see small relaxations, but not too much. And what you also see is that indeed the two water molecules that bond to the calcite surface are very close to the positions that correspond to bulk extension. So to a large extent, you can say that the water is simply replacing the oxygen molecules, atoms, that you also find in the carbonate groups of the calcite. I already mentioned that we wanted to see the effect of adding divalent ions, and so we did the exact same data set for relatively high concentrations of magnesium, calcium, and barium chloride. But to our surprise, to a certain extent, as you can see in the data, there is extremely little difference. I mean, it's not identical, but clearly overall, the structure doesn't change. Well, this was slightly disappointing because it disagrees with AFM results that predicted something else. We thought, okay, we're going to pick this up, but it's not the case. Apparently, the AFM, well, the conditions were not the same, but maybe also the interpretation of AFM is not as straightforward as one would hope is the case. So let's ignore the ions for now. Nothing is happening there. Let's continue with the system in water. And then we collaborated with Paolo Raitieri and Julian Gale from Australia, in fact. They really have state-of-the-art modeling capabilities, where they have different force fields, which are the fastest way to do computer simulations. In fact, they also developed a new force field very recently that should behave better. And brute force method, they also have been doing some DFT simulations, which are extremely computationally expensive, and so the amount of time you can simulate such a thing is limited, and so it's a combination of these things. Now, it's very difficult to actually, and also not useful, to directly compare the outputs from computer simulations with X-ray diffraction, because the computer simulations typically have lattice parameters that are significantly off from the X-ray diffraction, so you need some relative transformations to do a proper comparison. But I refer to the paper for the details about that. It's relatively straightforward, but it takes a little bit of time. And the thermal disorder that we find in X-ray diffraction, we can also derive from the computer simulation simply by taking a time average of where the positions are of the atoms. And so that allows us to do a complete comparison, and that's what I show here. So it's the same graph that I showed you earlier that you should recognize by now. But now it added the 3 different simulations: rigid ion, amoeba, and DFT simulations. And you can see, I think that's the first conclusion, that overall things are pretty much at the same place. In particular, in the bulk of the crystal. And if we assume that the X-ray diffraction results are the truth, which is always a little bit doubtful, but if we assume those as the reference, then we see that the difference in positions that we find for the different simulations are actually quite small. I mean, I think 0.05 angstrom is already an excellent agreement, but you clearly see that the DFT, the most expensive simulations, actually are even better than that. They have a deviation of, on average, only 0.02 angstrom. So excellent agreement, I would say. In the liquid part, which is of course the more interesting part, we see that the deviations become significant. You see the spread of the positions also in the graph itself. And if we take an average of the deviations here, we see that again, DFT is significantly better. And so it depends on the kind of problem that you address, how accurate you have to be. But then the rigid ion might not be accurate enough, but in many cases, I think something like the amoeba field, 0.1 angstrom. I mean, what is 0.1 angstrom among friends, you could say. So simulations are definitely trustworthy on that level. What also is nice with simulations is that you can figure out the dynamics of this, because the water here is definitely not fixed in place. And from the simulations, the residence time of one molecule is of the order of 4 nanoseconds. This, of course, something that would be nice to check with modern techniques like using an X-ray free electron laser. I think that this is possible in principle, although not easy. We did also did a direct comparison where we simply used properly transformed coordinates from the molecular dynamics simulations and compare them directly with the X-ray diffraction results. And you can see that, in fact, this is pretty decent. It shows that we're not missing anything, but obviously it's worse than our best chi-square value that we find for the optimization of our model, because this is non-optimized, and I would say that it shows that the agreement is quite nice. Just as a small add-on, we did very similar data, and I show it because it's very nice data, in my opinion, where we did not have the calcite in water, but in an environment mimicking oil. In fact, in this case, it was carboxylic acid dissolved in methanol. And what we found is that this quite strongly bonds to the calcite, where the carbonate group are in positions very similar to the water molecules I just showed you. And what is very nice, if you have long chains, they form a quite rigid layer. And as you can see from these crystallization rods, this is the 2O crystallization rod, it immediately shows that there's quite significant in-plane order as well. So this is a highly ordered two-dimensional layer. The shorter chains we learned are disordered. And with that, I come to my conclusions. And these are that I think we can say that we are slowly and finally reaching the stage where several methods can provide a consistent picture of a solid liquid interface. So that's good, because no single technique will give you the full answer. Although there is certainly more work to be done. I did not include the AFM information here because it's not so easy to see the images from AFM and understand exactly what it refers to, and it needs a more correlated structure, a study as simply so along the lines that we've done here for the calcite system. For the gallium nitride system, which I thought would be very simple, we learned that it's more complex than at least we anticipated. The calcite system, I think, shows that we have quite convincing agreement. And I at least think that the simulations that show such good agreement can also be trusted in areas where the X-rays are pretty useless, but which are very relevant for things like the growth dynamics of actual growth systems. And what we also see in these two examples, and that's actually something we've seen also in other systems, is that water shows much less layering, this slow progression towards the bulk structure than the metals. And that is all I wanted to discuss with you today, and I'm looking forward to any questions that you may have. Thank you very much.